Okay, people. Today we're going to be talking about fission and fusion, or how we can actually release some of this binding energy from a nucleus and use that to our advantage, or use that for energy production. So first of all, I'm going to talk about nuclear, not nuclear, nuclear fission. Fission is a fissure or a splitting of the atom. So this is the one that we were actually reasonably good at, reasonably successful at. Also the one that went kind of pear-shaped with things like Chernobyl, Fukushima and 3 Mile Island. A few of the important parts for the fission process are over here. A few of the important parts of the fusion are over here. So let's start with fission, the moderator. So the moderator is something that will actually help absorb some of the energy from the split atoms. So this thing will absorb energy. It will also help to speed up or slow down, kind of marginally, fractionally, some of this process. So when we're actually splitting, we're starting with some fuel, which is uranium 238. We need somewhere around about 2% of the fuel to be that. In reality, we've got about 0.7% is fissible material or fissile material, stuff that will undergo fission. So what we can do, or what we need to do sometimes, is to enrich this fuel. So what we're doing is filtering out what the 99 point something percent of it is, which is uranium 238, in order to have a higher percentage in the end of 235. What we're going to do is shoot a neutron at it. This neutron, we don't want to have very much energy. At the start it has heaps, at the start, where this neutron came from, I'll get to it in a minute, where this came from, it had heaps and heaps of energy. If it just had way too much to actually be absorbed by this uranium 235. So what the moderator does is absorb some of the excess energy from this neutron, and in order to absorb that, it has collisions with it. So the moderator in lots of nuclear reactors is actually heavy water that's made with deuterium instead of just normal hydrogen, and what that does is actually collides with that neutron. It sometimes will absorb it if it's not specifically heavy water, but what it will usually do is just take most of its energy, like nearly all of the energy. That means that our moderator, the heavy water, gains kinetic energy. Kinetic energy is heat. It transfers or absorbs lots of this heat, and then it can transfer that to a heat exchanger, boil some water, spin, turn it to steam, turn a turbine, make some electricity. So what we have is our fuel absorbs the neutron with a tiny bit of energy, and it will become uranium 236. Now this guy here is really unstable. It will undergo spontaneous fission after 10-ish seconds, give or take, about that many seconds. So what it will do is split, and when it splits, it generally forms barium and krypton. That's one example. It's a reasonably common example. What we need is for, I'm going to go this way, 36 and 56, or 56 and 36. So barium number 56, krypton number 36. It may in fact be the other way around. 56, 36 equals 92. So we're conserving the amount of positive charge, and we'll end up with a whole bunch of neutrons up here, but not enough. So 3 excess neutrons will disappear. These 3 neutrons just so happen to be this one here. So we have the opportunity to have 3 neutrons, so 1 neutron in, 3 neutrons out, and make 3 of these happen in the next phase. We don't want that to happen though, unless we're making a bomb, so we don't want that to happen. We want, on average, 1 of these 3 to be absorbed by uranium-92, which is why we only want a low percentage, and also why we want this to absorb a fair bit of energy. What it does is allows us to have something that's sustainable but also controllable in terms of a chain reaction. The products that we get are these 2, but any other combination that adds up to 92 will work, or is a possibility. These things are generally radioactive. I'm fairly certain that barium ends up, one of the isotopes is barium-141. So if you do a little bit of maths in your head, you can probably work out that it's got somewhere in the, what's that, 85 neutrons, 85, that's a lot. It probably wants somewhere in the high 70s, low 80s. I can't remember what the stablest one of baryum is. So it's got a few too many, which means that in terms of the, that graph, remember that graph, neutrons, protons, it's, up there somewhere. It's way above that line of stability. So it's going to undergo decay. Kryptons, same deal, that undergo decay, and they'll give off beta particles. So these two will give off beta minus. Some of the good things about it, it's kind of efficient. So we're not burning fuel, which is a chemical reaction. We're actually doing a nuclear reaction here, so it's more efficient. So the fuel is energy dense. So what energy dense fuel does, it means you don't need as much in order to make the same amount of power or generate the same amount of electricity from it. Bad stuff, obviously, because holy crap, we have radioactive stuff. So we have radioactive waste, I guess. And then of course there's, if it goes bad, Chernobyl, obviously a bit of a bad one. So as you can see, fission is a relatively simple process, I guess. We've had the technology to do this for quite some time. We're pretty good at it. There's well over, I think there's a few hundred nuclear reactors running this kind of setup with, may not be uranium, it might be plutonium, it might be something similar, where we're using neutrons to make an atom split. The splitting of that atom releases some of the binding energy in the form of kinetic energy here and here. This loses some energy to the moderator. The moderator turns that energy, transfers that energy to some water, turns it to steam, spins a turbine, just like the wind towers up in the hills. Alright, next colour. For fusion, what we need is to get some positive charges to actually fuse together. So fusion is fusing, or things that are sticking together. So they're not splitting apart, they're actually sticking to each other. So remember, the strong nuclear force, the nucleon force, will actually be an attractive one if these two can get close enough together. However, the electrostatic repulsive force is massive. So in order to overcome that electrostatic repulsive force, these two things need to be going really, really fast. Like near enough to the speed of light fast. In order to do that, they must be super heated. Alright, which is where this thing comes in. So these things are beyond the solid liquid gas phase. They're well into the next one, the plasma. So these things are so incredibly hot, and they need that temperature, that heat, so they've got lots of kinetic energy so they can overcome those forces that are trying to repel them apart, and hopefully they've got enough energy left over to actually fuse. And when they fuse, their mass defect is positive, so they lose mass by fusing the small things together, and you get a whole bunch of energy out of it. So these things are going fast to overcome electrostatic repulsion. Now the sun is hot and dense, and there's lots of pressure and there's lots of gravity. So the sun's kind of cheating. That's meant to be gravity. The sun's kind of cheating. The sun has lots and lots and lots of heat. Lots of heat. The sun is also dense because it's so massive that it's got this internal, huge amounts of gravity pulling everything in, which means that it's at a very high pressure. Pressure means that you've got particles that are really close together but trying to push apart, and all of this comes about because of its gravity. Now we can do this. We can't do these. Alright, so on Earth we can simulate the temperature of the sun in order to do fusion. However, we need to make our fusion hotter than the sun actually is to compensate for this stuff here. So we can't have something that's as dense, as high pressure, or has the same amount of gravity as the sun on Earth. Alright, what that means is that we have to contain it somehow, and the best way is in a toroid, a donut shape. Alright, so one of the more successful fusion reactors at the moment uses deuterium to make helium, or it uses tritium and hydrogen to make helium. Alright, and these products here are heavier than this one. So these two, same deal, heavier than this one. So you have more mass here than you have here. We lose mass, they're giving off energy. In order to make these things fuse, we need to have them compacted close together so that they will collide, or super hot or super fast. Best way we can do that is in a toroid. So we have charged particles of the hydrogen, we strip away their electrons, so now we've just got some protons and neutrons whizzing around everywhere together, and we have a magnetic field and an electric field. So the electric field will help us make them go faster, so hotter. The magnetic field will help contain them in a smaller space. And it's basically this thing here. We can't make magnetic fields, as strong as the gravitational pressure, I guess, of the sun. So we have to make them go faster than what we'd actually like, I guess. So the fuel that we're using is deuterium or tritium and hydrogen, and the products that we're actually making is generally just some helium. And this helium here isn't actually radioactive. It's actually pretty damn stable. There's another version of the same thing where we're making, we're using deuterium and we're using hydrogen, and we'll actually make helium-3. But this thing's actually quite stable too. So we're not making radioactive products like we were over here. It's also why I did that in green, and radioactive stuff green. The good things about it, it's energy density even higher, which is quite staggering. So per nucleon, this has way more energy than this one over here. But the bad one is the tech is out of reach at the moment. So we're trying to compensate with temperature for the fact that we can't do these things just as well yet. So this one here, fusion power, is it's the future. But whether I see it in my lifetime or whether you see it in yours is, I really don't know. I'd love to be able to see it, because then we have, deuterium and tritium is naturally found in seawater, so we'd be able to, power the planet, I guess, just using those sorts of things. So it's up to you which one of these in your head you actually kind of prefer. This one we can already do, and we do it pretty well. This one here we can't do yet, so we're somewhere, last I heard, somewhere in the 70% efficiency here, so we're getting 70% of the energy back that we're putting into the system. So we're having to make it too hot in order to compensate for this lack of density, I guess, which means that it's not viable yet. It actually takes more energy than it uses. This one, on the other hand, gives off a lot more energy than what it actually uses. Alright, thank you.